Okay, wall forms. This is it right here. This is a wall form. Okay, the wall form is made up of sheathing, studs, wales, and wall ties. So we've got same process. If you look at it, it's you're going to see a replication of a lot of things we did before. Unfortunately, the load doesn't come straight down. It's gravity driven, and I got to explain that first. Once we get the loading diagram put together, the rest should be something you ought to be able to grasp. So let's look at it. I'm on page 610. We're going to be doing a wall form example. I've got a 14-foot high wall, so I'm going to draw this thing as 14 feet. High wall. We're going to pour it at 3 feet per hour and 60 degrees Fahrenheit. So my rate of pour is 3 feet per hour, and the temperature of mix is 60 degrees Fahrenheit. Forms we use only once. Only once. It's a multiplier. Only once. That's going to be what you're going to see on a test. Only once or several times will be the words. These forms will be used only once, so stress is for short-term loading apply. We're going to use 7/8 inch plywood. So I've got right here 7/8 inch thick plywood. 4x8 sheets, 3,000 pound ties. 3,000 pound ties. Framing lumber, construction grade Doug fir larch construction grade, and purchased as required. Okay, first thing we need to figure out is the loading that is going to happen on the wall. Okay, I don't know if you remember anything from physics at all, but if you were to dive in a pool and go down 10 feet, the pressure on your ears increases as the depth. So in water, the force going down, the weight of the water over your head is equal to the weight of the water pushing in from the side. So it's a direct transfer, weight down. So if I wanted to, if this was water and I had a head of 14 feet, the pressure as I went down would look like this. Gets bigger as I go down. This is the height, this is the pressure. Okay? And it's gamma H. Pressure is just the unit weight of the water times the height over the top of you. So if that was water and it was 14 feet, it would be 62.4 pounds per cubic foot times the 14 feet. It's liquid. Okay. When we pour concrete, it's a liquid. Therefore, if we poured 14 feet of concrete and you wanted the pressure right at the bottom, right here, after 14 feet, this number right here would be gamma H. 150 pounds per cubic foot times 14 feet. So if I multiplied 14 times 150, I would get the weight of concrete over the top of me. That's 2,100 pounds per square foot. Okay, so that would be what we would calculate if we looked at concrete being poured fast enough that it remained a liquid. Okay, the ACI code says that's not the case. When you pour it, it's going to start hydrating. When it hydrates, it's going to start going from a liquid to a semi-solid to a solid. Therefore, as we pour, part of that liquid is going to turn into a semi-solid, therefore decreasing the horizontal load. So the table on page 512 gives you the maximum force that can be exerted on the form sideways. So if we look at that, go to 3 feet and 60 degrees. And what do you get? I get 600 pounds per square foot. Okay, so if you look at your book, that's what they've used. So 600. So I'm going to come over here and plot 600. P max equals 600 pounds per square foot. So even though if it was total liquid, you would have 2,100 pounds a square foot, with the rate we're pouring and the temperature of the mix, the maximum horizontal pressure is 600. So now, plot it. Draw a line straight up. That line is going to intersect the straight line curve gamma H. Okay, so my pressure distribution is going to look like this now. So I can erase this. This doesn't have anything to do with me anymore. There's the pressure. And how far down is a pressure going to become 600? Well, how many feet of concrete do you have to stack up if it weighs 150 pounds a cubic foot to weigh 600 pounds? So all we got to do, H prime, I'll call H prime. H prime equals P max divided by the unit weight of concrete. So 4 foot down is where that break happens. So this is 4 foot, that would be 10 feet. So inside the form, you've got this pressure pushing out, and you can see as it gets near the top, the pressure becomes 0. So right now I've got pressure pushing on this wall, and I'm going to do this. I'm going to make these long, make that a little shorter, make that a little shorter, a little shorter, a little shorter, and nothing. So it keeps getting smaller as I go. Now, we've got 3 elements there, 4 elements. We've got sheathing, studs, wales, and wall ties. Hopefully you can see this. Even though the sheathing has load on the bottom that is much more than at the top, we're not going to take and stagger the sheathing and make it smaller as we go up. So the sheathing is going to be dependent upon P max. The studs, even though theoretically we could put a stud in here that looks like this, actually it would do something like this. Nobody's going to take the time to cut the studs. They don't manufacture them like that. The studs are based on P max. Okay? Now, if you look at the wales and the wall ties, look at this wale. It's right here. If I have a wall tie, it's right there where the pressure is really big. If I go up to this wale, look at it. It's at a point where the pressure is small. And if I had a wall tie here, the pressure is small on the wall ties. So we're going to use 2 different ways of figuring loads. For sheathing and studs, we're going to use P max. For wales and wall ties, we're going to use the loading diagram. So we'll be using this guy for that. So we're going to go ahead and we're going to worry about designing the sheathing and the studs, and then we're going to move into the wales and the wall ties. So that's how you get. So our P max equals 600 pounds per square foot. Okay, we got that. We're going to use them only once. And I'm going to redraw this picture when we get to that point to scale, because we need it to scale. So let me go ahead and figure out what we've got. There's my loading. So what is this? This is W1. Okay, there's your W1. Okay, according to this, we have 7/8 inch plywood. Okay, I need my properties. What am I going to use for formulas? Well, we just figured P max is 600. Okay, if you go and you start looking at this, I'm going to get to where I know exactly what they've asked. They've asked me for plywood, the sheathing, L over 360, and let's see, what else have they asked me for? 1/16 of an inch, and then it's plywood, so it's rolling shear. So for this wall, I need this. This is sheathing. I need that. I need that. I need that. And I need rolling shear. Walls, plywood. So let me write them down. Plywood. I need bending. Square root of Fs over W1. Delta. And shear. And since it's a piece of plywood, that's rolling shear. So my rolling shear equation looks like this. Big L equals H IB over Q over 0.6 W1. Okay, do exactly the same as we have. Unfortunately, I don't have any of the data. So let's get it. Plywood, what do I need? I need F, E, H. I need S, I, and IB over Q. Okay, go to page table 4-2 on page 4-5 and go down to the plywood area, the very bottom. It says F is 1545. It says E is 1,000,005. It says H is 57. We don't have to worry about wet. It's already wet, it says. But we have to worry about this once only. Once only, increase durations by the following. It says increase the bending stress, increase the horizontal shear stress, and do nothing with this. So that's what they should have done. So let's look and see if what I say they should have done, they did. Look at the values for the materials. Where are we at here? Parallel, check bending. Here we go. There's the 1545 times the 1.25. I'm on page 610, about halfway down. 1545, and they ended up with 1930. And then, if you keep going and you keep looking at this a little deeper, they did nothing with the 1,000,005, and they multiplied the, you got 71. Okay, then go to table on page, let's see, plywood. Table on page 4-9, table 4.3. 7/8 inch plywood. What do we got? We got moment of inertia, 0.278. S, 0.155. 0.515. Okay, that looks good. And 8.182. 8.182. There's the, do I get them right? Let me go across here. That looks pretty good to me. There's my data. Do it. Same as we did before. Pop them in there, right where they go. So if we pop them in here, see what happens. F, 1930. S, W, 1,000,005. H, okay, those should match the handout. Hopefully they do. So I'm on page, I'm starting on page 610, and I get 1930, 515, 600, and get 1409. Okay, put that one down. Move on to the next page. Next page, I got the 1.69 is 1497. I move to the next one, and I get 1658. Then I move to the last one, and I get 1.61 feet. And I multiply it by 12, and I get 19.4 inches. Okay, that's what they got. This is a spacing of the studs. So the plywood itself denotes it's the spacing of the studs. So let's go. Spacing of studs. Littlest out of it is what? Looks like this one. So these studs are going to be spaced at 1409 max. Okay, let's see what they did to us. They said require, let's see, wall form. Okay, we're done with that. Got that page whipped. Let me put this over here. And it goes down, and it says rolling shear. Spacing of studs, bending moment governs at 1409 since we have 8-foot panels, 7 equal spaces at 13.7. It's more convenient to use 12 inches, so they decided to put them at 12 inches center to center. So even though we could have gone 1409 or less, they picked 12 inches. So this is what your handout said. Takes care of them. So studs are, spacing of studs are done. We've got 7/8 inch sheathing, studs spaced at 12-inch center. Let's go to part 2. Part 2 says, stud spacing at 12-inch center. We're going to use 2x4s, S4S for the studs. So they said 2x4 S4S. Okay, so now we're going to do a little bit of work. We can get rid of all this stuff. I still need those letters.